The next topic I'm going to talk about mutual inductance. Mutual inductance we indicate with the M, okay, measured in Henry. This is also same as self-inductance. The unit is same as self-inductance Henry. Now, the definition of mutual inductance is nothing but there is a definition written here, but I'm going to say it in a simple word, simple sentence. So if you keep two coils side by side, because of the current flowing in first coil, there is an induced EMF in the second coil. Okay, it doesn't matter whether you have current in the second coil or not. As long as current flowing in the first coil, there is an induced EMF in the second coil. So that property is called mutual inductance. So because of the current flowing in one coil, an EMF induces in the other coil. As long as we place these coils together, that mutual inductance is constant. It doesn't matter which way the current is flowing. That mutual inductance, some important properties. Here is the first one. Mutual inductance is the ability of one inductor to induce a voltage across the neighboring inductor. As I mentioned, that mutual inductance is constant as long as we fix the coils side by side. Now, that value does not change until unless you separate the coils. Okay, so that M value does not depends upon the current flowing in that coil. Okay, it always depends upon the distance between these two coils and how much flux is linking to the secondary coil. Okay, so that's the first thing. Second thing is mutual inductance is always between two coils. It will not appear between any other combinations like inductor and capacitor, capacitor and capacitor, capacitor and resistor, or resistor and inductor. So mutual inductance is always between two inductors, L1 and L2. So sometimes you might have zero mutual inductance because these two coils might be placed far away. So the flux is not linking with the second coil. Flux produced by the first coil is not linking to the second coil. Now, mutual inductance is always a positive number like a self-inductance. Next thing is the voltage produced by mutual inductance need not be positive all the time. Okay, now how do you define that mutual inductance? Okay, or the polarity of that induced voltage. How do you find the polarity of the induced voltage? We'll find it by using the dot convention. So the dot convention is nothing but in olden days, say if we have two coils side by side, okay, if you have two coils side by side, there is, we don't know the orientation of the coil. Orientation means this coil might be rotated in clockwise direction, this might be in anti-clockwise direction. That orientation is indicated by the dot basically. Okay, so the orientation of that coil, how these coils are wound across the core, that helps, that this dot convention helps us the polarity of induced voltages. Now it is useful to find the polarity of induced EMF in the nearby coil because of the current flow in another coil, in the first coil. So if current I1 is passing through this, we know that there is an induced EMF E, that E equal to N times d phi by dt. Okay, N is number of turns here, N2. Say this one has N1 turns, this coil 2 has N2 turns. Okay, so E equal to minus N2, minus is nothing but because of the Lenz's law, minus N2 times d phi. This phi is flux produced by the first coil which is linking to the secondary coil. Need not to be all the flux linked to the secondary coil. Okay, maybe half of it is only linking, so I would say phi 1 2, flux produced by first coil but linking to the second coil. Okay, this E2, induced EMF E2 equal to minus N2 times d phi by dt. Now so another way of writing this, I mean if you use the M format, I mean mutual inductance, E equal to m times di1 by dt, because we know that E2 equal to minus n2 times d phi 1 2 by dt. Now what I'm going to do, minus n2 times d phi 1 2 by di1 and di1 by dt. Okay, this minus n times d phi 1 2 over di1 is nothing but the mutual inductance M. But the mutual inductance does not depends upon phi 1 2. Okay, the mutual inductance depends upon what is the core we are using to connect these two coils and what is the distance between these coils. Okay, those things. Now the dot convention, please pay attention, this is the important point you need to know. If a current okay, let me read this point. The polarity depends upon the orientation of both coils and the current direction in the first coil. So the polarity of the induced EMF depends upon the current entering into the first coil as well as orientation of both coils. The orientation tells us where is the dot. Okay, now the important point is right here. So if a current is entering the dotted terminal of one coil, then the induced EMF across the second coil is E equal to m times di1 by dt, with the dotted terminal of the second coil is positive. So if a current is entering the dotted terminal, then the dotted terminal of the other coil is positive, with induced EMF E equal to m times di by dt. So let me find a place. Okay, so here is an example. So here is a coil. These two coils are given like this. So the mutual inductance always indicated like this. Okay, m value. Okay, so I1 is entering the dot. If current is entering the dot, that indicates that this is the voltage, supply voltage is V1 here. Definitely there is a self-induced voltage E1. Okay, E1 equal to L1 times di1 by dt. Now the induced voltage E2 here equal to N2 times di1 by dt. Okay, where N1 is number of turns on primary coil, first coil, N1 is number of turns on the first coil, N2 is number of turns on the second coil. Okay, so according to the definition, if current is entering the dotted terminal, then induced EMF then the dotted terminal of second coil is positive. Okay, so that's positive and negative, and induced EMF E2 equal to N2 times di1 by dt. As long as you understand this, I think you can easily solve half of this chapter. Okay, so for example, I have something like this. Here is the dot, another dot is right there. Okay, so what is the induced EMF in the second coil? Say that indicates that the mutual inductance between these two is M. Okay, so according to this, the induced EMF E2 equal to N2 times di1 by dt. Okay, with so current is entering the dotted terminal must be plus, so plus and minus. Now we understand the dot convention, so we're going to find the inductors are in series. So here what happens if two inductors are in series with the dot convention? What is the total inductance value? Now we know that, so to find out the total inductance here, let me see, here it is. Okay, now because of the current entering in the first coil, there is an induced EMF. I'm going to label that as V1 equal to L1 times di1 by dt, with voltage here, the induced voltage according to Lenz's law, okay, that oppose the rate of change of current. So if current is entering, the voltage up here across this will have positive terminal where the current is entering. Same thing here, we will end up with the V2 equal to L2 times di1 by dt, because same current is entering there. Okay, now we'll talk about mutual inductance. because of the current flowing in this coil, there is an induced EMF here. Okay, so current is entering the dot, so the dotted terminal must be plus. So plus and minus m times di1 by dt. Okay, and because of the current flowing in the first coil, there is an induced EMF here that will be plus and minus, because current is entering the dot, the dotted terminal must be plus, so m times di1 by dt. So what is the total voltage? V total equal to L1 di1 by dt plus L2 di1 by dt plus m times di1 by dt. Everything is positive because if you look at the polarity, every polarity looks like in series, m times di1 by dt. If I pull out di1 by dt, L total equal to L1 plus L2 plus m plus m. Okay, so this is nothing but L1 plus L2 plus 2m. Okay, so if current is entering the two dots, then the total inductance is going to be L1 plus L2 plus 2m. Now, if you have something like this, if current is entering one dot and leaving the other dot, like this. Okay, so here, because of the self-inductance, you see this is V1 equal to L1 plus L1 times di1 by dt. And here, because of self-inductance, L2 times di1 by dt. Okay, now current is, and I'm talking about the mutual, so here current is entering the dot, so the dotted terminal must be plus, so we'll end up with plus there, minus here. This is because of the mutual inductance, m times di1 by dt. Okay, so that's the voltage. Current here is, in this case, it's leaving the dot opposite way. All you need to remember one important statement. That one statement is, if current is entering the dot, the other dotted terminal is positive. If not, it is negative. So if current is leaving the dot, then that dotted terminal must be negative. So based on that principle, here current is leaving the dot, so here the dotted terminal must be negative. So what will be the total voltage here? V equal to L1 di1 by dt plus L2 di1 by dt minus m times di1 by dt minus m times di1 by dt. So the total inductance is L total equal to L1 plus L2 minus 2m. Okay, if the currents are, if the dots are opposite side, so what the dot indicates? The dot indicates the orientation of the coil. So probably this coil might be turned like this, another one is in the opposite direction. Okay, this is going in clockwise, probably this is going in anti-clockwise, something like that. Okay, so when the two inductors are in series addition, then L total equal to L1 plus L2 plus 2m. When they are in series subtraction, L1 plus L2 minus 2m. Now, when they are in parallel, when the two inductors are in parallel addition, okay, so because of the self-inductance, we have L1 times di1 by dt. Because of self-inductance, L2 times di2 by dt. So that whatever the current coming in, it's going to split I1 and I2. I1 current is flowing here. Okay, now current I1, because of the current I1, there is a mutual inductance, current is entering the dot. So remember, what is entering the dot? So here is the dot, my current is here entering the dot. I mean, the dot is where my current is entering. So that's what I meant. Okay, so here current is entering the dot. So another case here, so here the dot is at the end of the inductor, so current is leaving the dot. In this case, current is leaving the dot. Pardon me about my spellings. Okay, so current is leaving the dot. Now, So if you look at here, I1 is entering the dot, so the dotted terminal must be positive. So m times di1 by dt2. So because of I2, there is an induced EMF here, that m times di2 by dt. So current is entering the dot, so the dotted terminal must be plus. So what is the total voltage? V total is same, right? In parallel, it's same. So one branch has L1 di1 by dt plus m times di2 by dt. Another branch has the L2 times di1 by di2 by dt plus m times di1 by dt. Okay, now if you solve, so this is equation 1, I make the other one as equation 2. So if you solve those two equations, when they are in addition, this is how the total inductance is going to be: L1 times L2 minus m square over L2 minus m. When they are in addition, when they are in subtraction, it's going to be L1 L2 plus m square over L2 plus m. Okay, that is for the parallel. If two inductors are in parallel, that's for the total inductance with the mutual inductance. My apology, this one is when they are in, this must be minus though. Okay, so let me explain one more time. So if two inductors are in parallel, addition, so the dot is going to be on the same side, current is entering, so I1 is entering, I2 is entering, then this is the formula. Okay, now if we have dot on the opposite side, okay, here is the dot, here is the dot, but the current, one current is entering, another current is leaving. If that is the case, then L total equal to L1 L2 minus m square, so numerator is same, denominator is L1 plus L2 plus 2m. Okay, I'll stop this video here, so, and I will solve more examples in the next video. Thank you.